This is tutorial 4B, Laplace Transform, question number 6. We're given a differential equation over here. Initial condition y at time 0 is equals to 1. So this is t. Y times t equals to 0 equals to 1. Y dot 0 equals to 0. So y dot 0 is dy dt at time equals to 0. Now, we are also given that the input is unit step. We are asked to find yt. We'll use Laplace transform to convert this equation into the S domain so that we can manipulate the equation algebraically and then find the inverse Laplace transform for yt. So the Laplace transform of d2yt dt square, the Laplace transform is s square ys minus s y0 minus y dot 0. Let's substitute y0. y0 is equals to 1, y prime 0 equals to 0, and therefore we get s square ys minus s minus 0. So this is d2yt dt square. So this is the expression s square plus, sorry, we're not there yet, so let's still operate on this top expression over here that I have highlighted. Now let's operate on the second expression, 3 dy dt. 3 dy dt. So this is 3. The Laplace transform is 3 dy dt is sys minus y0. This is 3 sys minus y0 is, this value is 1, so it's minus 3. And what about 2yt? So 2yt, Laplace transform is 2ys. And what about xt? So xt, the Laplace transform is simply x of s. So let's substitute all we have found over into this expression. Please check. We now have the algebraic equation showing the relationship of y with xs. Since we are interested to find ys, because after finding ys, we will do inverse Laplace transform to find yt. So we shift everything onto the right hand side. So we have xs over, plus this expression here. You'll realize that this expression, all the values on the numerator is due to the initial condition. So because the initial condition is non-zero, that's why the numerator is non-zero. Actually, if the initial condition is 0, this numerator will become 0. What about the denominator? This denominator are common because it came from this guy over here. S squared plus 3s plus 2 is this. So let's try to verify this. This is s squared plus s plus 2s plus 2 is s squared plus 3s plus 2. So we have basically factored out this to show what are the poles of the expression for ys. So this is the pole. Alright, so once we have this equation over here of ys, we know that we want to perform inverse Laplace transform. To perform inverse Laplace transform, we perform partial fraction expansion and we would get the following expression. So by partial fraction expansion, you need to factor out all these factors, put it individually, and solve for the constant at the numerator. We find, and this you have to do it by yourself, b1 equals to half, b2 equals to 1, b3 equals to minus half. You substitute in here and you perform inverse Laplace transform. The inverse Laplace transform of this is simply b1 over s becomes b1 unit step. What about this one? B2 over S plus 1 becomes B2 E minus 1t. And the last one, B3 over S plus 2 becomes B3 E minus 2t. So we substitute and we find that this is our answer over here. Now when you look at this response, you'll realize that 0.5 ut is called the steady state response because when t goes to infinity, the output is 0.5. What about e minus t and e minus 2t? As t goes to positive infinity, this becomes 0, this becomes 0. So 0.5 times 0 is 0. Therefore, the steady state response is 0.5 and the transient response is that two term with the e minus t and e minus 2t. So now the second part of the question asks us to find the transfer function. The transfer function is defined as ys over xs, but with ys with 0 initial condition. So in the previous example, the initial condition was not 0. It gives rise to this part. So to have 0 initial condition, simply throw away this part, which is this part over here at the bottom. So you realize that when we throw away this part, this is due to the initial condition, at least the is. Is came from the initial condition. So when by setting is equals to 0, we have ys over xs, which is this expression here. And we can find the transfer function in the s domain, and hence we can find the transfer function in the impulse response in the time domain by simply doing inverse Laplace transform. To show you why is is due to the initial condition, we give you a hint in the next page. I extracted this from Chaparro's text, page 221. With that, thank you.